Good morning, everybody, and welcome to the DC preliminary of FameLab Astrobiology. I'm Sean Domingal-Goldman. I'm going to be your host for this morning. I'll be introducing our contestants, but before we get to that, I'm going to introduce our judges who have so graciously volunteered to provide their services to us today. I'm going to start on your right with David Grinspoon. Dr. Grinspoon is curator of astrobiology at the Denver Museum of Nature and Science and is an adjunct professor of astrophysical and planetary science at the University of Colorado. A frequent advisor to NASA, he is lead scientist for astrobiology on an instrument that is now on its way to Mars on the Curiosity rover. One of his books, Venus Revealed, was a Los Angeles Times Book Prize finalist, while another, Lonely Planets, The Natural Philosophy of Alien Life, was a Penn Literary Award for research nonfiction. His popular writing has appeared in Slate, Scientific American, Natural History, Astronomy, the Boston Globe, the LA Times, and the New York Times. He was awarded the 2006 Carl Sagan Medal for Public Communication of Planetary Science by the American Astronomical Society. Please help me in thanking David for joining us today. Next to David, we have Linda Billings. Dr. Billings is a research professor at the George Washington University School of Media and Public Affairs in Washington, D.C. She does communications research for NASA's astrobiology program in the Science Mission Directorate. She has also advised NASA's lead scientist for Mars exploration and NASA's planetary protection officer on communications. Her research has focused on the rhetoric of science and space exploration and the social construction of scientific authority. She earned her PhD in mass communication from the Indiana University School of Journalism, her MA in international transactions from George Mason University, and her BA in social sciences from SUNY Binghamton. Please join me in welcoming Linda to the FameLab stage. Thanks, Linda. And next to her is Bill Margol. Bill Margol is a graduate of Syracuse University's S.I. Newhouse School of Public Communications. He has worked for the last 23 years in many positions in the television industry. Covering the ground of writer, producer, editor, developer, and executive, Bill has worked at the Sci-Fi Channel, TNT, the Travel Channel, where he launched the groundbreaking series Anthony Bourdain, No Reservations, and Discovery Studios. In 2008, Bill joined National Geographic Television as Director of Development, and in 2011 took on the role of Vice President, heading up all development for National Geographic Television. Bill has a love of science and adventure, and in spite of that, the fact that he would most certainly lose his lunch in his helmet, dreams of one day being an astronaut. Please join me in welcoming Bill to the FameLab stage. And finally, next to me is Nikki Lowry. Nikki is Director of Film Marketing and Outreach for National Geographic Cinema Ventures. As such, she markets their giant screen and digital films to museums and science centers, as well as manages the education outreach for these films, with particular emphasis on STEM education. Nikki's experience spans education and entertainment marketing. She has served as film commissioner in Park City, Utah, as well as director of marketing for the Sundance Institute, the Sundance Film Festival, and the Miami International Film Festival. She has taught college-level English language and literature. Figures I get that part of it wrong, right? She has taught college-level English language and literature and English as a second language in both Thailand and Lebanon. She has been the senior marketing manager for the National Geographic Explorer Classroom magazine, which brings science content to 2 million students in grades K through 12. Please join me in welcoming Nikki to the stage.
There might be aliens in my backyard. I'm from Bozeman, Montana, and close to one of the hottest spots on Earth for astrobiology. Yellowstone National Park is home to some of the weirdest creatures found on Earth. These microbes live in pools of hot acid, geysers without oxygen or light, eat iron for food, and can survive temperatures near boiling. How do these extreme creatures, or extremophiles, relate to astrobiology? Scientists at Montana State University and around the globe study the microbes found in Yellowstone as analogs for creatures that might live on other planets in environments very different from our own. One important task of astrobiology is to determine the limits of life as we know it. We want to know the temperatures that life can survive, the chemical toxicity that life can withstand, and the nutrient ranges on which life can subsist. These conditions define habitability. The definition of habitability can help broaden or narrow our search for life in the universe. By studying the Yellowstone bacteria and archaea, we learn that microbes can withstand temperatures and chemicals that humans would deem uninhabitable. This volcanic hotspot has set our imaginations to aliens thriving on a seemingly extreme planet. Also, the microbes in Yellowstone National Park may be useful to answering one of mankind's longest and most important questions. How did life begin? To study this question in the field, scientists must first find an environment similar to what Earth was like billions of years ago. Back then, there was little oxygen, more volcanic activity, and a much warmer climate. This description fits some of the sites in Yellowstone where bacteria still live today. By studying these analogs to ancient life, we learn how the first organisms could have lived. This volcanic hotspot provides information that an origin of life due to iron-sulfur compounds is possible. This literal hotspot in my backyard is important to answering the big questions of astrobiology. How did life begin, and where can it exist in the universe? The aliens in my backyard may provide an answer.
That was great. I love the whole aliens in my backyard, the way you started that. And then, because again, that immediately engages the audience and helps them identify with what it is you're about to talk about. I love how you defined some of your terms, which I thought was very helpful, maybe because I'm the entertainment, non-science person, but it was great. I liked your use of gestures. I know you were a little nervous, but in spite of that, I thought you brought it off. Very expressive, and I think that's very good. So all in all, a good performance. Thanks.
I echo all of that. And I immediately felt that like I was in 6th grade or 5th grade and at an assembly and listening to a science lecture, and that's not meant to be that I think your demeanor and your presentation felt like it would be great for young kids trying to understand some real great science concepts. Good pickup when you forgot your place. It happens to everybody. Yeah. But you know what? You didn't let it stumble. You didn't let it. See, I just did it. You didn't let it throw you.
Thank you for understanding.
Damn. You didn't let it throw you, and you picked up and you went on. Not easy to do. So really nice. So great enthusiasm.
Ditto to what my fellow judges have said. And I thought your narrative was very well constructed. That's something that is of particular interest to me. And though this is not a criterion on which we judge people, I have to say you have a great stage look.
Yeah, I think the jargon police might give you a warning, but not an actual ticket, for a couple of terms you used, like archaea, that you didn't explain. But that's really my only substantive critique. I think you have really good presence, and you picked a great topic. And again, I love the aliens in my backyard and the way that you situated it with the fact that you live out there and you put a little bit of yourself, therefore, into the story in a subtle way. So it wasn't just about aliens, it was also about you, and I thought that was great.
Thank you so much. 3.5 billion years ago, something extraordinary happened. Life happened. How? Why? Where did it come from? Astrobiologists try to answer these questions by studying the origin of life. We want to know how life arose from non-life. What implications does this have? It has implications for other fields of astrobiology besides the origin of life and society at large. There's a huge knowledge gap in the history of our planet. The transition from non-life to life is not recorded. And we cannot go back in time Therefore, we can only experimentally investigate the events that change the face of the planet. We want to know what reactions brought us from non-life to life. Scientists around the globe do this via several methods. Dr. Michael Russell studies the abiotic, inorganic, non-living reactions to lead to an organism's metabolism and the building blocks of life. Dr. Lauren Williams traces the tree of life from now back to its ancestral roots, the last universal common ancestor. At my home university in Bozeman, Montana, Dr. John Peters studies the microorganisms in Yellowstone National Park as analogs for the earliest and simplest life forms on Earth. He reasons that because the conditions in certain hot springs of Yellowstone National Park are very similar to what Earth was like 3.5 billion years ago, these microorganisms could have been the first to live on Earth. He saw that the metals in the rocks in Yellowstone were mimicked in the cell's machinery, and probes into how these metals were incorporated into the microbe's metabolism, a possible key step in the origin of life, and one step closer to answering that big gap. The most exciting part for me is if we are able to show a route from non-life to life, then we can almost be certain that somewhere out of the billions of planets in the universe, that life has arisen from similar abiotic conditions. The more routes we find to life from non-life, the more certain we are that life has arisen spontaneously on Earth or other planets. We have learned that we are not special. Our planet is not special in terms of temperature, size, or contents. Why should it be in terms of life?
Very nice recovery from the alarm. This is one of those talks, I just want to compliment you, where after the talk I say, oh, I get it. And then tomorrow morning I'll try to tell my friend about it and I'll say, oh, I hate to ask Hillary, but good job.
Thank you.
Would you explain to our audience what analogs are?
Analogs are an example of something else that we can find here on Earth. So an analog for an origin of life would be organisms that we think could have been there at the origin of life. And an analog for life on other planets is a life form that looks like and seems like it could live on other planets.
Nice job. Very, very clear and good dramatic explanation. I'm sure one could talk at length about this, but real briefly, where does the 3.5 billion years come from? Why do you think that's how old life is?
Well, we have fossils that date back almost 3.5 billion years ago. And we know that Earth cooled down to be in a situation conducive to life a little bit before that. So we're kind of putting our estimate shortly before the first fossils, which were stromatolites. I don't know if anybody knows that word. They're these big rocks like in New Zealand where microbes are actually fossilized and you can actually see these mats of life that are billions of years old. Thank you very much.